Hello, my name is Maxime Rio and I'm working at NeSI and NeWA as a research software engineer. Today I'll show you how to use Dask in a Jupyter Lab environment to accelerate data science related tasks on an HPC. In particular, we'll see how one can use Dask to accelerate hyperparameters tuning of machine learning model on an HPC. But first, for those who missed Wolfgang's presentation about Dask, I'll give you a very brief explanation. So Dask is a Python package, and this Python package helps you use distributed computational resources, such as just the processes of your laptop. This is already distributed resources, but it can go up to clouds computers, and for today's case, HPC nodes. And for today's presentation, I'll use, to execute the code, I'll run it in a Jupyter Lab instance. And in particular, this instance is already running on the HPC, and that's a service soon to be provided to NeSI's users. And if you're curious and interested about it, please contact us and you could be part of the testing user. Okay. So for today's task, I will use the very famous and beloved MNIST dataset. So I've already loaded the dataset to spare some time. So here, what you can see is the typical samples from this dataset. So these are images of digits from 0 to 9. And of course, the task consists of given an image, tell which number is represented. And because it's a supervised task, I've split it in a train and test dataset. And to keep it quick, I've used a very small training dataset, 5,000, and a bit bigger test dataset of 10,000. And as a baseline algorithm, I'll use a multi-layer percentage classifier coming from the very nice and famous scikit-learn package. And if you don't know about it, so scikit-learn provides a wealth of well-implemented and robust machine learning models in Python. And so here I'm just fitting it with the training data without any parameters tuning. And what we get as a baseline accuracy is 93% accuracy, which is already quite good. But to be fair, also, MNIST task is not that complicated. Okay, but could we get better results? Yes, actually, the multi-layer percentage model has a bunch of hyperparameters, which is good to tune to get better performances. And in this case, I want to optimize the size of the hidden layers, also some penalization of the weights and the learning rate. So to do so, I will use a random search strategy, which means I will just sample random configurations of the hyperparameters, and I will assess their performances and keep the best performing one. So I defining first a search space, which is how you sample this. And I will use a meta estimator also from scikit-learn, which is a randomized search CV. And what it does is basically for each of the sample configurations, it will do a cross-validation to get a more robust estimation of the performance. But again, only using the training data, never touch test data. And here I use only 10 configuration to be a bit faster. Okay, but the cross-validation is 5-fold. So in total, I will have 50 models to fit. And this is what's called an embarrassingly parallel task, which means that each of the models does not depend at all on the other models to be fitted. So we can run them on different computers or nodes or whatever. So here we use Dask to do this. And to use Dask, you need first to instantiate what's called a cluster. And again, this could really be just your local machine, could be a local cluster, but we'll use the HPC. And to access the HPC, we'll use a special type of cluster, which is the Slurm cluster. So let's just instantiate it. And once you get a cluster, and I'll get into the details of it in a moment, you bind it to a client, and the client will be the part of your code which actually deals with submitting tasks and retrieving results. And the client says here, I mean, the address, and there is a dashboard, but more importantly, it tells us that the cluster has no workers. So nothing that can execute the code we want to submit to it. So first thing we'll do is we'll ask the cluster to scale up and have 20 workers. But I will show you a bit of what's happening in the background for this specific cluster. So when you're on an HPC running Slurm, you have a queue of jobs, and when you submit some task, it goes into the queue, and when there is some free resources, it gets scheduled on them and executes. And what you see here is a view of the queue restricted to only my jobs, because otherwise there are just thousands of them. You can see at the moment that I have two jobs running, and one of them is this interface I'm using for running the demo. And as soon as I'm hitting the cluster scale, what happens is I have new job schedules on the cluster. And fortunately, what you can see is they're already running, so they didn't have to wait, and I was lucky enough that they got scheduled right away. Okay, so now the cluster is ready to receive task. So how do we access this and submit it? So you could actually do it via the client object, but what is interesting is actually Dask is quite a good citizen in the ecosystem of the numerical packages in Python, and in particular, it can be used by Jobly. And for those who may not know, scikit-learn, when it has a parallel task to execute, will use Jobly to distribute this task on a backend. And so here I'll just say to Jobly, okay, by the way, use Dask and use this. So this specific scattering just means that it will pre-send the data to avoid multiple copies and save a bit of bandwidth. Okay, so now it has started. And what's happening here is basically that the 50 feeds are being scheduled. But it's more interesting to show you exactly what's happening. So for that, I will use a small extensions of the Jupyter Lab, which is dedicated for Dask. And it gives us a view on some of what's happening in the background. So here I'll just prepare three little things and progress. Yeah. Okay, so in these panels, what we see are the following. The top panels contain the stream of tasks which are being executed on the cluster. And here the tasks are only fit and score, so there are many of them happening in parallel. The task progress actually is an overall view of all of the things which are currently schedules on the cluster and not yet executed, so you can see what are the pending tasks and the to be completed. And the final panel actually, which is the task workers. I mean, there are more panels, as you can see, but these are the one I wanted to show you. This one gives you precise information about the workers themselves. And so you can see, okay, we have 20 of them. You can see where they are with their IP. You can see that they have 5 threads each. So something I did not highlight it when I started the cluster here is I asked for 10 cores per jobs, and I asked for 2 workers per job. So if you go here, you can see that we have 10 jobs, and each of them have 2 workers, hence the 20 here. Okay, you can see also the CPU load, and here you can see that a lot of them are just idling, and one is still working hard, but the other ones are doing nothing because basically their job are done. And you can finally have a look at the memory consumption, which is very good to know when you're about to blow the worker's memory, and maybe you should ask for. Okay, so it took about 2 minutes, and now it's done. Let's have a look at the performance of this. Okay, that's already better. It used to be 93, now we're 95% accuracy, and we can also have a look at the best hyperparameters that have been. This is good, but actually the random strategy is not the best. We can do something slightly better. So the thing we can do is we can use another algorithm called hyperbands, which will make a better use of the time budget. This is provided by another package called DaskML, which is a layer on top of Dask specialized for machine learning, hence the name, and provides a set of meta optimizers and also other convenience object. And the other thing I need to do here is I replace the randomized search CV by the hyperbands, and I just have to start it right away without having to specify anything but Dask because it's relying on Dask. Now, what is it doing? So I'll explain while it's running. So the hyperband algorithm, compared to a simple random search, will sample many configurations, roughly 200 in this case, and run them for a bit of time. But it needs your estimator to support a partial fit methods, which means that you can fit it with just um, a sub part of your data, just small sample. And after doing so, it will evaluate which one are the best one and only continue fitting these ones and discard all the other ones. Which is why, if you're looking carefully at the diagram on the top, you see that it's becoming sparser and sparser because actually less and less models are competing with each other and continue being fitted. And at the end of this, we'll only have one of them, and this will be the winner, which should be hopefully the best one. And okay, so it took about 1 minute, and we can have a look at the performance. So it's about the same as previously. But the cool thing here is we explore many more configurations, so we can be more confident that we correctly explore the space of the hyperparameters and have a good one. Okay, but what now if you want to do deep learning, right? It's not, I mean, scikit-learn is fantastic and I really love it, but maybe I want to do something which is not there, unfortunately, like a convolutional neural network. Okay. And I want to, of course, I want to fit it on the GPU because it will be fast. Okay, so what do we need to do? So first, um, we'll use the same elements, but we need a cluster which runs GPUs. So I will first I will close the current running cluster, and you can see that no corresponding jobs are left in the queue here. And I will start a new cluster. And this new cluster actually have one small difference, which is I request GPU resources uh, for each of the jobs. And for each of my jobs, I ask for just one worker. So I will have one worker per Slurm job with a GPU associated. Okay. And once I have that, I will again schedule workers, but this time I use an adaptive strategy which consists in asking for at minimum one worker, and if there is more workload, it will go up to four workers, so using 4 GPUs and no more because I can't use more. But again, if there is less workload, it will deschedule and go back to the base of one. Okay, that's for the cluster part. Now for the model part, I'll use a part source model, which is defined in a separate file, and all of this will be made available. So if you want to look at it, but this is a very simple convolutional neural network with 2 layers and a fully connected layer, a bit of dropout. But I want to use the hyperband because it's very nice. So what should I do to do that? Well, actually, it's simple. Hyperband expand your estimator to fit the scikit-learn API, which with a regular PyTorch model does not. But there is a nice project called Scorch, and with Scorch you can just wrap the neural network, and then you have an object which is compatible with scikit-learn API. And I explained this while it's running. And you can have a very similar thing with Keras, with a project called SciKeras, which is similarly can help you wrap the model into a scikit-learn compatible object. Okay, so here I'm also running the hyperband search, but this time it's using the new cluster. And what you can see now is suddenly it dropped to, it jumped to 4 workers instead of 1, which was idling. And you can see that they're not fully using the CPUs here, which is normal because actually fitting is happening on the GPU. And just for the additional details here, I'm optimizing the number of channels for the conventional layers, the number of units for the fully connected layer at the end, the amount of dropout, and the learning rates for the Adam optimizer. Okay. What is interesting here is you'll see that at the end of the fit, the workers will become deschedules as they're useless, which will happen soon, I believe and hope. Yeah. So here you can see already 1 is gone because it's not useful anymore, and soon the other ones will go. Yeah. up, and we can finally, so it took about 1 minute, and we can see we can see the final accuracy of this convolutional neural network, which is better than the previous models, and we have the corresponding hyperparameters. Okay, so with this, I will conclude now. Okay, so to summarize, what have we seen today? So we have seen how to do interactive work on the HPC, because everything which has been presented was happening in a Jupyter Lab instance, but running on the HPC. We've seen how to start a Dask cluster, which uses Slurm as a backend to do all the distributed work. And once we have this cluster running, we have seen how to use it to run all the embarrassingly parallel task of a scikit-learn meta-estimator, which was a random search. Then we've seen how to use a slightly more advanced meta-estimator, which is Hyperbenz, to make a better use of the time budget. And this being done, we have restarted a new cluster, but this time using GPUs, and we use that to fit PyTorch models on this cluster using a nice wrapper to make it also scikit-learn compatible. So all of this have maybe been displayed a bit quickly. So if you want to try it yourself, the code will be available on NeSI's GitHub. And of course, if you have any question, please contact me by email or questions or comments at maxime.rio@nesi.org.nz. And as a final comment, I'd like to add that I'm part of the consultancy team at NeSI. And if you liked what you've seen and you want some help to develop or accelerate some code on the HPC, don't hesitate to contact us, and we'll see what we can do for you and how we can give a hand. Thank you.